So we have been able to discuss quite a few things in this chapter. We have discussed page rank, div rank. Even before that, we discussed some simple approaches to measure the link, right? So in this lecture, we will discuss another important metric or quantity called SimRank. And the intuition of SimRank is very different from say page rank or related measures. So here the idea is that two objects are similar if they are related to similar objects. Now the difference between page rank, div rank and this kind of SimRank kind of methods is that page rank, div rank, they basically produce ranks of nodes, ranking of nodes, right? It basically measures the prestige of a node. It is a node centric measure, whereas SimRank is a measure for a pair of nodes, for a pair of objects. Okay. So the idea is that two objects are similar if they are referred, they are related or they are cited by similar types of nodes. Okay. So here what is the idea? The idea is that we are measuring the similarity between a pair of nodes, right, and our task is to return those pairs which are similar, whose similarity values are higher. In other words, say for example you are given a node and you are asked that, hey, look at other nodes and tell me that out of the other nodes which 4 nodes are similar to the given node. Okay. So your node is given, so what you would do, you would basically measure the similarity between this node and this node, these and these, these and these, these and these, and so on and so forth. You can't do this thing using page rank, right? So therefore the SimRank kind of approaches were proposed. So given a network of size n, you need to compute n square such similarity measures. Okay. So here is the idea. So this is the network, and say let's say this is a citation network, okay, and node E cites papers C and D. Therefore C and D, although they are not connected to each other directly, but they are related because they are cited by the same paper E. Node H cites both B and G. So B and G are related because they are cited by same paper H. Okay. What about A and D? So A, if you look at the the papers who are citing A, you have C, F and G. So the neighbors of A is C, F and G, but neighbor of D is what? Neighbor of D is sorry, this is neighbor of B. Okay, this is A and B. Okay, so neighbor of B is D and H. So there is no neighborhood intersection. Since there is no neighborhood intersection, one may say that A and B are not related. Okay, but if you think carefully, they are related in some ways. For example, B is cited by H, right? G is also cited by H. Okay, so B and G are somehow related. Okay, now G is citing A, so in indirectly H is also citing A in 2 hops, right? Now therefore A and B are cited by G in some ways. So G is citing A and B are cited by H in some ways. So H is citing B directly, H is citing A indirectly. So in that sense, A and B are connected, A and B are related, similar. Okay. Now how do we do this thing computationally? So let's assume that there are 2 quantities. If the graph is directed, then you have inward edges and outward edges, inward neighbors and outward neighbors, right. So IV is the set of inward neighbors and OV is a set of outward neighbors. Okay. So these sets, so this node, this node, this node, these are inward neighbors of V and these are outward neighbors of V. Okay, outward neighbors of V. So the similarity between A and B is 1 if A and B are same, because an item is similar to itself with at most quantity, and that is 1. Okay. If IA and IB, meaning the inward neighbor of A or the outward neighbor of B, any of these sets is empty, then this is 0. You can't compare, right? Let us say there are 2 nodes, right, something like this, right. How do you compare between these and these nodes? Although they are related in terms of their outward neighbor, but they are not related in terms of the inward neighbors. Okay. So we are discussing this thing in terms of inward neighbors. So otherwise, if this set and this set are not empty, then the similarity of A and B is the sum of similarities of all their neighbors, all their pairwise neighbors. What do you mean by this? Let us say okay, so this is A, this is B, this is C, D and E. Okay. So I of A is I of B is C, D, E. Okay. Right. So I take all pairs of inward neighbors, meaning I will take C, D, C, E, D, D and D, E. So this summation, the summation would be over all pairs. You see here double summation and their similarities. So similarity between CD, similarity between CE, similarity between DD, similarity between DE, and then you take the sum. Okay. And then you normalize it by the total number of pairs. So how many pairs are possible? So mod IA times mod IB, right? In this case 2 times 2, right? Forget about the C, I will discuss what is C. Okay, C is a constant, I will discuss what is C. So this is the similarity. Okay. Now let us make it even more concrete. What I say is that I start with a similarity. So here S and R are same. Assume that S and R are same. Okay. So I denote S. I denote similarity by R. So similarity at zeroth iteration between A and B is either 0 or 1. If A and B are same, then 1. If A and B are not same, then 0. And over time you basically update it, right? And this is the updation rule. If A and B are same, then 1. If A and B are different, then the quantity that we discussed, and then we repeat it. We stop when R of k plus 1 AB is kind of same as R of k A comma B. Okay. And if you have a kind of a bipartite network, say you have users and products, right, you can use the same quantity. Okay. So you say that so this is product. So a product is basically the similarity between two products is the similarity between users who have bought these two products, whereas the similarity between users is the similarity between products which these two users have bought in the past. Same ways, right? So similarity between users is the similarity between products. Okay. Here outward neighbors of users is basically products. You see, these are outward neighbors for a user. Okay. And for a product, you basically look at the inward neighbors and their similarity. So, two users can be considered similar if they buy similar products. Two products can be considered similar if they are bought by similar users. Okay. Let us take an example. Say this is a graph and bipartite graph, and you have users A, B, you have products K, L, M, N, okay, and you want to calculate the similarity between A and B. So, for node A, what are the outward neighbors? K, L, M. So, OA is K, L, M, OB is L, M, N, right. For product I, the inward neighbor is A, product L, AB, product M, AB, product N, B. Okay. So, now the similarity between A and B is basically, we look at these two things, all pairs. So, similarity between KL, KL, KM, KN, right, LL, LM, LN, ML, MM and MN, 9 pairs. Okay. One term is missing, this is MN. So, I need to calculate all these things, all these numbers one by one, and this is normalized by this one 3 times 3, some C1. Okay. So, now let us look at this quantity. Okay. So, let us let us look at this one. Let us look at S of let us look at the easiest one. This is the easiest one, S of LL. This is 1. This is also 1. Okay. So, what is S of KL? Let us try to understand S of KL, the first quantity. So, S of KL is some sort of C2, right. So, K and L, their inward neighbors are A and B. So, this would be S of AA, KL, right, K and L. So, AA and AB, AA plus S of A comma B, and this is 2 into 1. Okay. So, C2 into 2, this would be 1 and this would be S of AB, which you do not know, right. So, C2 by 2 plus C2 S A comma B by 2. Okay. What is S of KM? S of KM is same as we look at K and M. So, same pair AA and AB. So, this would also be this one. Okay. So, this is done, this is done. Now, let us look at S of Kn. S of Kn means you have this and this. So, you have only one pair AB, right. So, S of Kn is C2 times S of AB. Okay. Try to understand what is happening. So, I am writing all this similarity in terms of S of AB. S of KL is a function of S of AB, S of Km is a function of S of AB, S of KL is a function of S of AB. Right. Now, let us look at S of LL. This is one. What is S of LM? S of LM is AA, AB, BA, BB. S of LM, right? So you have all pairs. So let me check. S of LM, right? LM. Okay, so S of L and M. So L and M, L and M. So you have basically same pairs, A and B. So you have AA, AB, B and BB. Okay, you can also write in terms of S of AB. Okay, so if you think about it carefully, you will see that all these similarities can be either one or a function of S of AB. Okay, so finally, S of AB, I mean if you add everything, you will see that S of AB would be, I mean if you when you add and move all S of AB to the left side, you will get this one, right, based on C1, C2. Now C1, C2 are constant that we can fix. Let us say C1 is 0.8 and C2 is also 0.8. This is given. So therefore S of AB would be 0.547. Okay. So this is the idea behind SimRank. Now what is this C? The C is something that allows you to, let us take an example and understand. Okay. So say this is A, B, C, D, E. So the similarity between A and A is 1. The similarity of B and C is basically would not be 1 because this is maximum. So would be something lesser than 1. Now this lesser factor is this constant C. So this ranges between 0 to 1, and let us say this is 0.5. So similarity of BC is C times similarity of A. So 0.5 into 1 is 0.5. So the similarity of AB is less than similarity of AA. Similarity of DB, similarity of DE is what? Similarity of DE is C times similarity of BC, and that is C square times similarity of AA. So it was C here, this is now C square. So 0.5 times 0.5, which is 0.25. So this C kind of gives you lesser and lesser weights as you move, further from A to the to the given node to the rest of the nodes. This factor C actually ensures this thing. Okay, and C can be defined based on your requirement. All right. So this is about SimRank. Now we are almost at the end of this chapter, and we will discuss the last metric called PathSim. Okay, and this is based on something, a very interesting idea is based on something called heterogeneous network and metapath. Okay, so what is heterogeneous network? Heterogeneous network you already discussed. Nodes can be of different types, edges can be of different types. Okay, so V is the set of nodes, E is the set of edges, right? A is the set of different node types. It can be papers, authors. R is the separate edge types, citations, co-authorship, and so on. And then you have a mapping which maps a node to a node type, and there is a mapping which maps an edge to an edge type. Okay. Now if mod of A equals to 1, meaning that you have only one type of nodes, right? This is node homogeneous. If mod of R equals to 1, this is edge homogeneous, and if both of them are greater than 1, then this is both node and edge heterogeneous network. Okay. So think of this user product bipartite network. this is actually node heterogeneous network. You have different nodes, user nodes and product nodes, but edges are same. All these edges indicate some sort of bi relationship. Okay. So, and this is a kind of a edge heterogeneous network where nodes are users, but edges can be friendship relation, can be family relation, can be colleague, and can be anything, right. So, edges are heterogeneous. You can have both nodes and edge heterogeneity. For example, citation network, nodes can be papers or authors, links can be citations or co-authorship, and so on. Okay. So, on the heterogeneous network, we define something called network schema. Okay. What is network schema? Network schema is a relationship between node types, not nodes. The schema is defined on the node types. Okay. You basically say that, say you define a schema like this on a citation network, which means that an author can only be connected to a paper through citation, through the edge type write. So, author can write a paper. A venue, a publication venue can be connected to a paper through the relation publish. A keyword, a key term can be connected to paper in terms of contents. Paper contains the term, the particular term. So, this is basically a network schema. So, network schema is basically is giving you an idea about how different types of nodes, different node types are connected through which types of links. Okay. You can't connect an author to a term. You can't connect like this, it is not allowed, because the schema has to be defined earlier, and then based on the schema you can create your network. Okay. Those who have studied DBMS, this is very related to entity relationship diagram, ER diagram, if you remember correctly. Okay. There also you have entities, they have relations, you have schema, right, and so on. So, now we define a new concept called metapath. Okay. Metapath is same as path, but on the heterogeneous network. Okay. So, metapath of length L, this is defined by a composite relationship of length L, and the metapath is defined on the network schema, not on the graph. Okay. If I say that there is a metapath from author to paper to author, meaning I am indicating this metapath. Okay. If I say so this metapath has a certain semantics, APA. What does it mean? This paper, this author has written, this author has written this paper, and this author has also written this paper. So, this APA relation indicates the co-authorship relations between these two authors. Okay. Let us say there is another metapath, author to paper to venue to paper to author. So, author has published this paper is published in this venue, say this venue is CKDD, right. This paper is also published in this venue, and this paper is written by this author, meaning that these two authors are not direct co-authors, but they tend to publish papers in same venues. Okay. So, these metapaths, different types of metapaths indicate different semantics. Okay. So, if I say that say there is a metapath of length 3, there is a metapath of length 3 from between author between A1 to A3, meaning there is a node type A2 and the link, a particular link type R1 and R2. Okay, so therefore it's a composite relation. It's a composition of all the relations. So in this case, the relation is author, right, published or whatever, published relation or written relation, write or written relation, and this is also write or written relation. Remember one thing, that if there is a link from A to author to paper and the relationship type is write, there is another link from paper to author with the relation type written by or write inverse. Okay. There is relation from venue to paper through publish. The same relation exists from paper to venue with the link publish inverse or published by, and so on, right. So if I tell you that when I move from author to paper, am I be allowed to move from paper to author? Yes, through this link. Okay. If I say that there is a meta path of type this one, author, writes paper, contents term, right, contents term, content inverse paper, right, written by author, this is also possible. Okay. So when I say that I am interested in APA kind of meta path, it means that in the original graph, in the original heterogeneous graph, I am interested in all such path which connects two authors through a paper relation, through a paper node. So now in the original graph, you have author 1, author 2, author 1 and author 2 are connected to paper, through paper 1, right, author 7 and author 8, author 7 and author 8 are connected through paper 5. So I am actually referring to all those paths which follow this metapath APA. Okay. So I can also count the number of instances of the number of paths of this type APA, right. So hope you understood what is metapath. Now we define called path count. Path count, it basically indicates the number of path instances P which begin at X and ends at Y. Okay. So I say that I am interested in path like APA. So I can easily count the number of such paths in the original graph which starts from an author and it ends with an author, and at the middle we have a paper. We can count it. Random walk. So we can define all bunch of things on the now on the heterogeneous network using this metapath concept. Random walk, you can say that okay, I want to start from node X, I want to follow a particular type of metapath PL, right. So what is the probability that I start from X, I reach Y following the metapath PL? So in this way you can also measure the similarity. Similarity between two nodes X and Y using random walk is basically the probability of existence of a path P of type PL. We take the sum. Pairwise random walk. Pairwise random walk, the idea is same as random walk, but here the idea is that you basically start from two different nodes. So again similarity between X and Y given a particular intermediate node Z. So what is the probability that I follow a particular metapath P1 from X and I reach Z following P1, and what is the probability that I follow P2 and start from Y and reach Z? In other words, what is the probability that I start from X, follow a metapath P1, reach Z, follow a metapath P2 inverse and reach Y? what is this combined probability? This is called pairwise random walk. Okay. So path count, random walk, you can define, right, in this particular aspect. Now we define something called PathSim. So what is PathSim? So PathSim is a measure of similarity search scoring and ranking in a heterogeneous information network. It basically uses the notion of metapath. Okay, a metapath of the form, as I already mentioned, metapath of the form AL inverse. So say I move from x to y with PL, and then I move from y to x with the metapath PL inverse, right? And this is called round trip metapath. Okay, because you follow the same metapath and you move from x to y and then y to x. Okay. So now PathSim between two nodes x and y, okay, is defined by the total number of round trip paths with respect to x, total number of round trip paths with respect to x, total number of round trip paths with respect to y, and how many paths are there from x to y. Remember, these paths are all metapaths. Okay. So we look at, we say these are two nodes. We look at all types of metapaths and let's fix a particular metapath. Okay. So we basically want to understand how many metapaths how many round trip paths are there. Round trip metapaths are there for x, because we already defined what do you mean by a metapath PL. I follow PL and I come back x, right? It may move from x to z, x to p, doesn't matter. So how many such round trip paths are there which actually start from x and follow the metapath and again come back to x? How many round trip paths are there for y, starting from y, moving through some nodes and again come back to y? And how many such metapaths actually how many such round trip paths cover both x and y? Okay, and why too? Because when you count this one, you are basically double counting things. Because for y, let's say there's an edge like this, round trip edge, round trip metapath like this. So for x also you are counting one times, for y also you are counting one times. You are double counting. Therefore, the denominator is divided by 2. Okay, because in the numerator you are counting one time. Okay, so this is the formulation. Now let's look at an example. Okay, so let's say we are interested in this type of metapaths: author, Venu, author. We have these authors: Mike, Jim, Marie, Bob, and Anne. And these authors published papers in SIGMOD, VLDB, ICD, SIGKDD. These are different conferences. Okay, say Mike published 2 papers in SIGMOD, one paper in VLDB, 0 paper in ICD, and so on. So the task is that given Mike as an author, who are the similar authors of Mike? Find the authors who are similar to Mike in terms of publications. We are only interested in author, venue, author, metapath. Okay. So if you look at the visibility of, think of the graph, right? So in the heterogeneous graph, you have one entry called Mike, you have another entry called Jim, you have another entry called Mary, right? You have Maud, is also bipartite network, right? VLDB, ICD, something like that. And there are 2 papers. So Mike published 2 papers in SIGMOD, meaning that you can think of these 2 edges. right? So how many, so how many round trip paths? Remember, in the denominator we need to count this one, right? So when I measure the similarity between Mike and Jim, I need to count the round trip paths for Mike and the round trip paths for Jim. How many round trip paths are there with respect to sigmod for Mike? This and this 1, this and this 2, this and this 3, right, and this and this 4. Okay. So, right. So, how many such round trip paths are there? 2 times 2 with respect to mod, with respect to VLDV 1 times 1, ICD 0 plus 0 times 0, and KDD 0 times 0. So, we got the denominator. So, this is 2 times 2 plus 1 times 1. Now, we are interested in similarity between Mike and Jim. What about Jim? 50 times 50 plus 20 times 20. Okay. This is denominator. How many pairs are, how many such paths are there? We start from Mike and end at Jim, right? And follow this follow sigmod, for example. Think about it. So 50 is difficult to explain. Let's assume that, right? Let's assume that you have 2 edges here and there is 1 edge here. So Jim has published only 1 paper in sigmod and Mike has published 2 papers. How many round trip paths are there? This is not round trip path, starts from Mike and ends at Jim. So you follow this path and you come here. And second time, and another path, you follow this and come here. How many? 2 times 1. So here in this case 5 times 50, 2 times 50, 2 times 50 plus 1 times 20, right, plus 0 plus 0. So this is the similarity between Mike and Jim. Okay, this is the similarity between Mike and Jim. Similarly, say Bob, do the same thing. The denominator would be, in case of Mike and Bob, 2 times 2 plus 1 times 1 plus 2 times 2 plus 1 times 1. And numerator would be 2 times 2 plus 1 times 1, 2 times 2, 1 times 1. Okay. So if you do these calculations, what you will get? You will see that the highest similarity is between Mike and Bob, which is 1. Okay. Let's see. What about Mike and Jim? Look at this, Mike and Bob, the rows are exactly same. So they should be similar. But if you look at Mike and Jim, rows are kind of identical, but the quantities are very, very high. So they should not be same. So this denominator penalizes the fact that one author publishes more papers and other publishes less paper. Okay. Therefore, between Mike and Jim, you see that the similarity is pretty less, 0.082. Okay. Right. So this is the idea behind PathSim. So if you want to read about PathSim, this is the paper that you definitely go through. So this ends this chapter on link analysis. We have learned many things. We have started off by connecting, network science path related analysis with social science theory. Then we looked at simple measures, then we also looked at balance and status theory. We then moved into the metrics like page rank and div rank. Then we looked at SimRank, PathSim, and how you can use Metapath heterogeneous information in the node analysis, particularly for node importance calculation and node similarity measurements. Okay. I hope you understood this chapter, and in the next chapter we will discuss community analysis, and we will understand how this edges play an important role in community detection. And the next chapter we will discuss link prediction. There you will see how exactly all these methods that we discussed play an important role for recommendation for link prediction. Okay, thank you.